Subscribe now.
Welcome back to our digital signal processing tutorial series. In our previous tutorial, we explored the discrete Fourier transform, which is the DFT, right? We explored the DFT and how it can be used to analyze and process discrete time signal in the frequency domain. So while the DFT is a powerful tool, as you witnessed, it can be computationally intensive for larger signal sizes, especially when using the direct computation method. So in this video, we are going to delve into the fast Fourier transform, which is the FFT, an algorithm that's revolutionized the signal processing by significantly speeding up the calculation of the digital or discrete Fourier transform. The fast Fourier transform is based on divide and conquer approach, which breaks down the discrete Fourier transform calculation into smaller and more manageable parts that can be solved easily. So first of all, the FFT algorithm improves efficiency. That is, the FFT algorithm reduces the computational complexity of calculation of the DFT from the various signals, right? So we are going to show you how this method is able to reduce the number of complexity in calculating the DFT. And also, as I said earlier on, it is based on the divide and conquer approach, right? And this divide and conquer approach or algorithm divide the DFT calculation into a smaller DFT, which are then combined using some specific mathematical formulas, as we have already talked about, which is the trade-off factor. This approach reduces the number of complex modification required, right? So someone may ask, what is the use of fast Fourier transform? So there are some kind of applications that we use fast Fourier transform for. So the fast Fourier transform is widely used in various applications, including audio signal processing, right? Image processing, communication, and science. So without wasting much time, what to expect in this tutorial would be that we will discuss the basic concept behind the FFT algorithm and how it differs from the direct computation of the DFT. We also explore the divide and conquer strategy, which is mainly the butterfly diagram in the FFT and how it will lead to more efficient computation. And also, we will demonstrate the step-by-step process of calculating the FFT for a simple signal to illustrate its effectiveness, right? So let's go ahead straight away and then start everything. As I said earlier on, the FFT is a very efficient method for computing the DFT coefficients, right? And it also reduces the number of complex multiplications and complex additions, right? The only thing that's the algorithm, or the only barrier or the restriction that this algorithm faces, the sequence should consist of 2 to the power m, right? It should be at the power of 2. That's the only barrier or the only restriction on this algorithm. Aside that, there is no restriction for that. For example, the number of samples can't be 3. It can't be 5. So the number of samples should be in a powers of 2, right? That's the only restriction for this algorithm. So the number of samples can be 2, 4, 8, 16, 32, and so on, 64, right? Yes. So that's it. And then one thing that's I want you to also understand is that the number of complex multiplication in DFT basically is illustrated as n power 2, right? And then the number of this complex multiplication. And then complex addition, it's also done at n minus 1, right? There's complex addition. So now, when we come to the FFT, this reduces the number of complex multiplication and number of complex addition to a very low number, right? So in that case, when we come to FFT, the number of complex multiplication reduced to n over 2 log of 2 of n. And then the number of complex addition is also reduced to n log of 2n. Yes, n log of 2n. And the number of stages to perform such algorithm is also equal to m, which is equal to log 2n. This is the number of stages. So please, let's try and keep this one on our fingertips. These ones are very important. Before we proceed, I would like us to check on some few properties of Treadle factor. And these properties are the periodicity property and then the symmetry property. So first of all, let's look at the periodicity property. So for the periodicity property of the Treadle factor, talk about the fact that the Wn of k, let me use a different pen so that it becomes simple for you to visualize, says that omega n of k is equal to exponential negative j 2 pi over n and k. And in one of my tutorials on DFT, when we were using the Treadle factor algorithm over there, the linear transformation method, we talked about this, the fact that omega n equal to this very coefficient, which is the exponent negative j 2 pi over n, right? And then the periodicity states that when you have the Treadle factor n with the power of k, and when you add time sequence to it, which is the period, you are going to get the same thing, which is n, right? Let's look at something. When you say something is periodic, like signal, which is periodic, what does it mean? So when we say a signal is periodic, it means that it repeats itself at a regular interval of time. And this repeating pattern is also called a cycle. And the time it takes to complete one cycle is what we call the period. So for this n that I added here, I could have made the n equal to t. By the way, n is okay because I personally represent the n in a digital domain. So n it's in the analog domain. I use t for it. That's what we call a signal being what periodic. So now let's look at the property. The property says that when you have the Treadle factor to the power n and you add the period to it, it's equal to the same Treadle factor. Let's try and prove how this came into existence. We know that omega n is equal to exponent negative j 2 pi over n from our previous tutorial. Therefore omega n k is equal to exponent negative j 2 pi over n, and then multiply by k. So when we have omega n k plus n, it's equal to exponent negative j 2 pi over n, and then k plus n. Right, so let's try and multiply through. So when we have omega n k plus n is equal to exponent negative j 2 pi over n k minus j 2 pi over n n. This n will cancel this n, and now we have omega n k plus n to be equal to exponent negative j 2 pi over n k, and then here's plus into bracket negative j 2 pi over, there's the n has already been cancelled, so you don't have to bring it. So basically, let me get this one out first. Yeah, so from the law of indices, this addition here, we can also split it into two. So when we split it into two, we are going to get omega n k plus n equal to exponent negative j 2 pi on n k, and then multiply by exponent negative j 2 pi, right? So with this approach, when we compute this one using the calculator, we will get 1. Or if you don't want to use a calculator, you can use the complex plane. Here it's 1, -1, j. You can use the calculator for that. So pi, it's 180, 2 pi is 360. So when we start from here, pi is here, and then 2 pi is here. It means that exponent -j 2 pi is equal to 1. And therefore, we can say that this evaluation of this exponential function is equal to 1. So we can write it as nk plus n, and then it's equal to exponent -j 2 pi over nk, and then multiply by 1. And we are all aware that this omega nk is equal to this function over here, and this function is the same as what we have gotten here. Therefore, we can write that omega n of k plus n is equal to omega k of n. So this is a proof for the periodicity property of the trade-off factor. So let's move on to the symmetric property. For the symmetric property, it states that when we have the trade-off factor, right? We have the trade-off factor with the power k plus the number of cycle over 2, right, is equal to the negative of omega n to the power k, omega n to the power k. So let's quickly go through to derive how this one came into existence, because we'll be using them a lot. So looking at this, when we have omega n of k to be equal to exponent -j 2 pi over n of k, then we can say that if our omega n of k plus the number of cycles divided by 2, we are going to get exponent -j 2 pi over n multiplied by k plus what? N over 2. So doing the analysis, we can simplify the right hand side function, which is -j 2 pi on n k, and then plus minus j 2 pi over n multiplied by n on 2. So this n will cancel this n. So we can finally get us exponent -j 2 pi over n k, and then plus into bracket -j. These 2 will cancel these 2. Well, then we have what? Pi. And at the end of the day, we can write that omega n k plus n over 2 to be equal to exponent -j 2 pi k over n multiplied by exponent -j pi. Looking at this, if you don't have calculator, you can use the complex plane to do it, as I did earlier on. Here is 1, j, -1, and what? -j. So here it's what? Pi. From this equation, cos theta plus or minus j sine theta, we want the real part. So cos 180. Cos 180 will give us -1 from this quadrant. Or if not that, just look at the pi here. Move to pi and we hit on -1. So we hit on -1, we can say that omega n k plus n over 2 to be equal to exponent -j 2 pi k on n, and then multiply by -1. But we are aware that this exponential term here is equal to what? Omega k, and therefore we can say that omega n of k plus n over 2 is equal to negative omega n of k. So in my next tutorial, we are going to look at ways in which the fast Fourier transform could be computed, and we will look at it in the radix 2 fast Fourier transform algorithm. And these 2 fast Fourier transform algorithm, it's one decimation in time domain, which is DIT, and 2 decimation in frequency domain. Which is DIF. So thank you for watching and see you in my next tutorial.